And there we are. So last time we finished our, well, actually last time we already talked about the virtual machine. We finished our interpreter the week before that. And our first assignment was to implement the value array and the value stack pointer, i.e. the value stack. But first of all, to figure out what kinds of operations we need to do on the value stack to implement all our instructions. And so let's take a look at the VM spec again. Let me look at that in Markdown. There we go. So if we look at the instructions, it turns out that all of the instructions always operate on relative slot numbers. And some of them read and some of them write and some of them do both. So basically we need a way to address the stack with relative slot numbers. We don't even need to implement absolute addressing because that never happens. And really the only other operations that happen is that the value stack pointer is incremented when a call happens and it's decremented when a return happens. And if we have those four operations implemented, we can implement the whole VM. So that's basically our value stack abstraction. So let's write some prototypes for that first. And I'm going to put that into vm.c. Yes. And these don't even have to be public in the sense that they're still internal to the VM. One thing we are going to make public, though, is we're going to define some type of VMT. So I don't want global variables lying around. And we'll see later what we have to put in there. And maybe we need some VM init. We probably need that. VM. All right, so we said we need a load. So let's call that VS load, and we need a VS store, and these take, obviously a VM and a relative offset, and I'm going to use size t slot, and what it returns is an int64t. And the VS store returns nothing, and it takes a VM and a slot and an int64t value. That's the value to be stored in that slot. And then we're going to have a void VS. Should I call it push and pop? Because it's not really pushing and popping anything. Value stack. Yeah, let's still call it push because I'm too lazy to think of another name. And it takes an int64t amount for and number of slots. And the same goes for pop and slots. And we're actually going to implement all of these, and we're going to make them static inline. So that means that first of all, we need some kind of, we now actually need an array, and we need a stack pointer. So that's what we're going to do here. And we're going to make those. So this is going to be the value array, and the stack point, the value stack pointer is also going to be an s size t stack pointer. And now for reasons, value I'm going to call it get slot. So here's the thing. I want to be able to check that my accesses are within the bounds of the array. The thing here, however, is that well, actually, I can call this size t, but I don't think it matters much. So, but the problem is that the actual, so this is a relative slot, right? This is a relative slot, and to get to the absolute slot is the VM stack pointer plus the relative slot. But since I'm fiddling around with signed integers here, it's actually not trivial to do the check on whether I will end up with an offset that is within the bounds without first going to the actual absolute offset in unsigned arithmetic. And so I'm gonna do this addition here without any checks, which means that it can overflow and give me a preposterously large positive number, or a preposterously large negative number, which is then cast into a preposterously large positive number. And I'm going to relegate the checking to this function, which just takes an absolute slot, which I know will be at least, which cannot be negative, so I don't have to worry about that. And all I have to make sure is that the absolute slot, and actually I need to size t stack array size. So by the way, I'm also lazy and I'm implementing a fixed size stack, which means that if I run a program on it, it can lead to a stack overflow. But the stack overflow will really just lead to this assertion failure. Of course, means that I shouldn't compile without assertions, and that's not actually what you should do. But again, I'm lazy. But all I need to do is that the absolute slot is less than the array size. And then I can return the VM value array of apps slot, the address of that. Is that plausible, what I'm doing here?
Yeah.
Does that make sense? So I'm returning
above zero.
Huh?
That is not negative.
Because it's a size t.
This is an unsigned integer.
Oh, sorry. Yeah. Okay.
So it cannot be negative.
Right.
And now all I need to do here is return dereferencing getSlot this. Of course, I should probably cast it. And all I need to do here is rel slot do this equals value. Make sense?
Mm-hmm.
And now vs push just means that I'm incrementing.
I think there's one closing bracket missing.
A closing bracket where?
In VS Store. VS Store.
Like 10 lines down. VS Store.
Oh,
You're right.
Here I'm just incrementing the stack pointer. And here I'm decrementing the stack pointer. And I don't really have to check for overflow here, because the only thing that the stack pointer is used for is to later index the array. And I'm checking that indexing the array works. Right?
You don't ever edit the size.
No, I do not edit the size. So what I'm going to do is when I init the VM, well, array size, stack size, whatever. When I init the VM, I get a stack size. So I'm going to say VM value array equals malloc size of int64t times stack size. Now note, bad things can still happen, and this is how DVSC is. And I'm not going to do all the checks to make sure that they can't happen. But let me finish this. svlib.h. That's where malloc lives. So let's say I can download a VM file from the internet, and that file specifies how big the stack can be, and then it also specifies the VM program. The size of the stack here is given in number of slots, and the slot size is 8 bytes. So I multiply the stack size by 8. And then I set the array size to the stack size. Is it possible that, assuming that this allocation is successful, is it possible that I end up with a stack that is of a size that is smaller than the stack size specifies?
If you phrase it that way, possibly. I
Okay.
wouldn't think so, though.
Huh? Well, can you think of how that would be possible?
Not quite, unless he's lying to us, and I don't know. No, not really.
If the stack size is like bigger than like what you have in RAM, for example,
then malloc will fail.
It will fail.
Yeah.
But then
If I'm requesting more than I have memory for, then it will fail. Yes.
is it possible to? I mean, not just memory, but like, could you request something that overflows, like it goes into like the program memory for like the like how it's, you have the stack and then you have some space allocated for the program instructions and all that stuff. Is it possible to say malloc and then it would give you?
No, malloc will not give you memory that overlaps with any other shit.
Also, but like if we allocate a lot of memory in the heap and then keep calling functions, which gets put on the stack, that the function overlaps with the heap, that is possible, right?
Which function?
Like if we, I just I don't know which.
Like interpreting.
I guess like one function that gets called a lot. Because I just heard that there was once a virus, I think, where the program would like override the heap then with another code. Well, okay, that goes into another detail, but I think is that maybe does that maybe have to do something with that?
Well,
The question.
here's the thing. This check, or the whole reason for this check, is so that we don't overwrite the heap, right? We assume that we have this many slots allocated, and if we have this many slots allocated, we are allowed to overwrite them.
I think he's talking about like when you're actually, for example, the VM is running and it has its stack, and then like imagine if, as you're interpreting the VM, you have like a Stack Overflow and you're writing onto the heap because the stack overflows.
Which stack?
The stack of like the interpreter.
Our interpreter, first of all, that's not how Stack Overflow works. When the stack overflows, your program crashes because the top of the stack is guarded. Like the end of the stack is guarded by memory protection. That's the first thing. Second, our interpreter is going to be is not going to be recursive. It's going to be iterative. There will be only loops. There will not be any recursion.
Okay.
Well, I'm trying to figure out how you could get a smaller.
Okay. What if stack size is 1 shifted by 63 bits to the left plus 1? How much memory do I allocate? How much memory do I ask malloc to allocate?
Like 0?
How do you arrive at that?
No. Wait 1 second. Oh jeez, not binary. Wait, how many bits are in size T?
64. We're assuming we're on 64-bit machines.
Okay. So it's like the. Oh jeez. So that number would be basically like in binary it would be a 1 at the very beginning and a 1 at the very end, right?
It'd be like the largest negative number you can get, -1, right? But then that, no, actually, sorry, because it's unsigned, it would just be half of 64, or 2 times 60. 2 to the
Okay, guys, you're thinking way too complicated. This is ridiculous. Okay, the number I'm making here, right?
Too large.
Let's say this is 64 bits. Okay, let's just assume I don't want to count.
Yeah.
Okay, let's assume this is 64 bits. Actually, let's not assume. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So this is 64 bits. The number I'm constructing is 1 at the beginning and 1 at the end.
Okay, right.
Right?
Yeah.
If I multiply this by 8,
Oh, damn it. Okay.
what happens?
I see.
It gets really small again.
You're just like shifting it to the 3 bits, for example, and then you lose.
I'm shifting it 3 bits to the left.
Yeah, so then you
But
lose the top one.
This 1 goes away because it's shifted out. Right? So it becomes
Yeah.
zeros. So I'm deleting 3 bits here and I'm adding 3 bits here. And I end up with 8.
Yeah.
So I think
So fucking-
I've allocated a lot of memory, but really I've only allocated 8 bytes.
But like that's like a lot. Oh no, okay, no, I get it. Yeah, yeah.
But 8 bytes is not. I think malloc will find 8 bytes for me. It will happily find 8 bytes.
Sure it will, yes.
So
Okay.
we are going to assume. I'm not going to do a check here because again, we're assuming that all our programs are correct and everything. We're not doing error checks. I'm just saying if you program in C, shit like that can happen. So, like, don't program in C, basically. But since we're programming in C, let's ignore all the problems.
It's not too late to switch.
Huh?
Oh, nothing. Sorry.
Okay, so the last thing is we need to initialize the stack pointer, and the stack pointer is 0. So we start at 0. Also, another fun thing that happens with C is that when you call malloc, it will give you back memory that is uninitialized, meaning it can be anything. So what I'm going to do is I'm going to do memset VM value array. I could also use calloc. Why don't we use calloc? Oh, so actually, calloc might actually have a check for that. Contiguously allocated memory is filled with bytes. We could actually try that just for shits and giggles. But so calloc, I don't know why they have a different API for calloc than for malloc. But calloc actually will return zeroed memory. And what you can give it is you can give it a count and a size. So I can give it the count here and the size. And it might be possible that calloc actually does that check and will not give us a small array if we want a really large one, if we want an impossibly large one. Again, maybe we'll try it. Okay, so that's pretty much our VM interface. We can write a function. We're going to call it VM test. And it takes a VM. So how are we going to test the VM? Ideas? Well, so far we're not testing the VM. We're testing the VM test value stack. We only want to write value stack tests just to make sure that everything's on the up and up. What do we test?
So I guess just
load.
Okay, we have to
Load
test store
and
and load, sure.
Maybe load and then store. I mean store, then load to make sure that you get the same thing back.
We do one store and one load.
That's first. I mean, you want to do multiple, you could do multiple. Yeah, I guess you got to do multiple.
Okay, so how about we do define n, let's say we define n to be 1024, and we do is for int I equals 0. And I'm using all kinds of types, like I shouldn't use different types all the time. 0 less than n I plus plus. So what I'm going to do is first I'm going to write VS. I'm going to store VS store VM
VM store, right? Or is it VS?
II. It's VS for value stack.
Oh, sorry. Okay.
So at relative slot I store the value I. And then I assert that what I load at I is I. And then what I can do is I can test the push and the pop. Right? So what I can do is, let's say, let's define M to be, I don't know, 32. And let's do the following for int 64t. Let's call this the offset equals 0. And what we're going to do is, first of all, we're going to test that everything is correct. And then we're going to do VS push and slots. And actually, we're going to do the following. We're going to do int 64t off equals 0. We're going to push J, and if I push J, then the offset increases by J. Right?
Mm-hmm.
But now what I need to account for is that I need to subtract the offset here. And also this is stupid because it has to be I and not 0. Right? Does this make sense?
Yeah.
Sorry. Let's try that, and then we'll add a test for pop. So we're pushing in ever increasing. We're pushing by ever increasing amounts. So we're pushing 0 first, then we push 1, then we push 2, then we push 3, and so on and so forth. And we're going to call this VM main. We don't even have the context here. Yeah, we have nothing. Never mind. And VM main is static void VM main. Make a VM. We're going to init the VM with, I don't know, 2K. And then we're going to do test value stack. And sources vm.c. And let's see what happens. Oh, I forgot stdint. Implicit declaration of VM test. Oh, yes, because stack also in vm.c. I think it's std, right? Oh. And put the compiler. Okay. At slot VM. What? Oh,
Pass in the VM.
I need to pass in the VM, obviously. That was that. Unused function use pop. Yes, we haven't used it yet. So, ta-da! That's quite surprising. This is the VM, so that sets the pop as well. So now we have the same offset. So let's do the same thing in reverse. Which doesn't actually happen. So here we're pushing, we're going to push 31 last, but now we're going to pop
31 first.
No, we're going to pop 0 first, and then 1, and then we're going to pop 31 last. So we're kind of like pushing and then popping the opposite way, in a way. But this should still be, it should still work the same way. Oh, that's interesting. Oh, because I did not decrease the offset. So that's good. Caught a bug. There we go. Looks pretty good. Actually, let's. Oh, goddamn! I still don't. I need to install GDB. LDB, Simplang. Break. VM test. Value stack. Breakpoint. Yeah, I don't know how this works. Ah, there you go. Okay, run. Here we have a backtrace. Can I do breakpoint in line 57 maybe? VM.c. Okay, continue. So now we should be able to, if we look at the VM, we should be able to see value array. So we see that the stack pointer is 0. And you see that we've written the numbers in there. This should be 0. This should be 1023. So that works. And I hope you trust that all of this also works. So yeah, that's it pretty much for assignment 2-1. Is that about how you implemented it?
Okay. I think I have understood it a little differently. I thought we were supposed to like look at all the instructions, like move, add, and return and such, and like implement those as functions.
Oh, you did that already.
Well, I guess I did the stack then a little differently. I'm not quite sure actually.
How did you do the stack?
Do
you want to look at the code?
Oh, I'm scared. Yeah, sure. I think I sent you the link.
So is this updated with your new understanding?
Yeah. So I completely rewrote it and took some
So there's
inspiration.
VM and VM instruction.
Yeah, so I wasn't.
Oh, why does this
Well, yeah,
one?
I wasn't quite sure how to do that. In VM, what I just did before was I did. Okay, no, we'll get to it later. So I thought we just have the list of instructions and then the program counter and stack and everything.
Okay.
Then, so below in 23, when we initialize the virtual machine,
Mhm.
I tried to find the functions to each instruction, just to make it then work a little quicker.
Oh, okay. So you're getting ahead of the whole thing. You're implementing the instructions as each instruction as an individual function, which
Yeah.
and you store the addresses of those functions, basically. You store pointers.
So the length of the function array is the same length as the instruction array, pretty much.
Okay. But that's a thing that we'll get to later.
Okay, yeah.
So
So I guess
yeah, this is our load, right? This is
the write in line 91.
When is an arg ever absolute? Oh, absolute means that it's a constant.
Yeah.
Oh, okay. Right. Yeah. I mean, really, this is the main thing that we've implemented, right? And then we also had, yeah. So there you increase the stack pointer.
And then it return it.
You pop the stack pointer there. Oh yeah, I saw that you did it a little differently, which is valid.
Okay.
So you basically implemented almost the whole VM already.
Okay.
Kinda.
Oh.
Well, the only the main thing you're missing now is just the parser for the VM.
Yeah, I think I did that in the VM instruction.
Oh, you did that. So are you missing anything?
Well, I guess just running the things.
What are the things?
Like if I have the instructions and then just getting the virtual machine to run, that's not implemented yet.
Well,
you know what I mean?
You mean the driver that just calls the code to read the instructions and then run the VM?
Yeah. So the VM isn't doing anything.
Okay, but that should be like 2 lines of code, right?
Yeah.
Well, why don't you try that? And then you should be able to run. There's in examples, there's 8 queens. Queens, no. Oh, maybe that's not. Maybe I haven't committed that. Oh, there's next prime. Next prime simple. Let's see if that's in the git add next prime simple.sbc git status. Yeah, no, that's in the repository. So if you look at examples, there, next prime simple. So this is the VM code for next prime.
Okay. Yeah.
So if you try running that, you should see whether your VM works.
Okay. Cool.
And then you can even try how much faster it is compared to the interpreter.
Yeah. One thing though, do the instructions always take the same type of arguments? So like to differentiate between absolute values and relative values, because I think you only for set and jump and call, I think you're using relative values, and otherwise it's always relative, right?
No. So what you call relative values are slot numbers,
Yeah.
and what you call absolute numbers are constants or
Mhm.
immediates.
Yeah.
All of these instructions, when they say slot, it's always a slot, right? You can't make source. Source is never anything other than a slot.
Okay.
The only way actually to get... Okay, let's just go through it. So these are slots. In set, this is a slot and this is an immediate. So this is always a constant, right? This is just a number. So you write the number into that slot. All of these three are slots. All of these three are slots. These are slots. These are slots. This is an instruction index. This is a slot, and this is an instruction index. This is an instruction index. This is a number that gets added to the value stack pointer. And this is a slot. This is a slot. All of these are slots. All of these are slots. And that's it.
Okay. So, okay, yeah, that makes sense. Because then I could actually just ignore the $sign, right? Or is it just for better
Yeah, the
readability?
dollars are just, I don't know, stupid syntax.
Okay, yeah.
So I guess that means we should maybe, let me see what the assignments say. So the next assignment would be to basically write a parser. Oh, no, not even there. We should just bunch a few of these together because they're really, really simple. So the next one is really just do this, like implement the thing that this instruction would do, you know, using the previous stuff. It basically means load from -3, load from -2, then do an addition, and then store to 0. And then after that, that's the parser. And only then do we even start implementing proper instructions. So I guess what we could do in the next week is to do these three. Right. So this is really just to get used to the fact that VM instructions do very, very little. Like they do almost nothing, just a little thing. And this is, you know, parsing the file, and this is, oh, we can actually write a very simple program now that takes numbers and adds them. Okay. And then, yeah, and then the week after that, I guess we can do this stuff. And then the only thing we're missing is call and return, and then we're done with the VM, and then we can start writing a compiler. But I guess you'll be done with the VM maybe tonight. I don't know. There's probably going to be a bug in there.
No.
Find it. So you'll have to write simple test cases, and you know.
Yeah.
You know how it works. All right.
Okay.
I guess we're done then. So yeah, good work. And
thank you very much.